Let's go and get started. So thank you to everyone for turning in the homework. This was a simpler problem than it looked. So the problem was we had a series of planets from levels from 0 to 3. And there are transfers from planets on each lower level to the planets at the next higher level. So there are transfers from 0 to 1, from 1 to 2, from 2 to 3. But there aren't any transfers in any other direction. So you can't hop levels and you can't go back levels. So the first thing I asked was what kind of a graph this is. And it is a, let's see, directed, weighted, simple, and acyclic graph, because we've got weights here that tell us how expensive each transfer is. And so the question we wanted to know was, what is the cheapest way to get to a level on the third, or on the last, or a planet on the last level? So either this planet or this planet, and any path of transfers you can take from the starting planet. Okay, so we talked about a shortest path algorithm, Dijkstra's algorithm, last week. And so that says, given a starting point, it gives you the shortest distance to every other point in the graph. So I asked you about the time complexity. The time complexity depends on how you implement it. If you implement it using a poor method, it's order v squared, where v is the number of vertices, which is too slow. If you implement it using a Fibonacci heap, which is a pain in the ass to do, but you can do, it's much faster. If you implement it using a priority queue, which is how I described it during lecture last week, it's order v plus e log v, which is perfectly fine for this application. So that is a way to do it, and it works just fine. But we can do better than that. We don't have to use Dijkstra's to solve this. We can use a dynamic programming approach. And what that's going to do is exploit the particular ways in which these transfers are connected, which is that if we know the costs to get to the next to last level, maybe we've filled these in already and we know it costs, the minimum cost to get here is 3, the minimum cost to get here is 2, and the minimum cost to get here is 1, we don't have to, we can ignore all of these transfers when we're looking at getting from here to here. We only have to look at the transfers between levels 2 and 1. And that suggests that we can do a dynamic programming solution of basically filling in the minimum cost at each level, only examining the transfers from that level to the next level. So we can walk through this. We'll start off, it costs us 0 to get to the starting position. And then we look at the costs to get to the next level. What's this one? 15. And this one is 5. Okay. And then we can ignore these, because we already know the cheapest way to get here. So the cheapest way to get here, we can either start at this planet, minus 5, and get here in 10, or we can start at this planet, where it takes 5 to get there, travel along this transfer for a total of 15. So the minimum cost there is 10. Here, what's the minimum cost? 18. And here, minimum cost? 45. And then, same deal, now we've got this whole level filled out. So we can go on to the next level, which is 11 and -1. And then we just look and say, okay, this is the cheapest way to get to the highest level. So this is all we have. This is order v plus e. It's much faster because we don't actually have to store the graph. In fact, if you look at the code that I've given you, you see that I'm just reading in the transfers in order from level to level and calculating this minimum cost array on the fly and then updating it, which leads to much lower memory storage and much faster running time. So I kind of gave you something tricky. You didn't actually have to use a graph theory algorithm to solve this problem. You could use the good old dynamic programming stuff that we talked about several weeks ago. But thank you to everyone who turned that in. Pretty much everyone made a good stab at it. A lot of people did try and keep using the Dijkstra's algorithm, which works perfectly fine and kind of missed this one. So that is, that's how to solve this one. Okay.
Doesn't Dijkstra's have problems if you try negative weight edges?
It has problems with negative weight cycles, but because this is acyclic, it'll still work here. Okay, so that was the homework. So we are done with graph theory. We took 2 classes to discuss that. The topic this week is computational geometry. And before we get into the details of exactly how we're going to do this, I actually want to go into a little bit of the history of the geometry because I think it's really interesting. It is by far the oldest type of mathematics. So most of the rest of the algorithms, discussions that we've had over the last several weeks, those are all things that have been developed in the last 30 or 40 years since the development of electronic computers. Geometry is millennia old. It's one of the oldest forms of mathematics. And in fact, if you look over the doors right there, you'll see an inscription that I put up that was the same inscription that was over the doors to Plato's Academy 2 millennia ago. Does anyone know what it says? Anyone heard this one before? It says, "Let nobody ignorant of geometry enter here." You were required to know geometry as being part of a learned person to go to the academy. And so prior to the 17th century, all of this geometry that people were learning was what we call now synthetic geometry. It was probably the kind of geometry you learned in high school if you took your geometry class then, where you've got shapes, circles and lines and points, and you're learning about constructive proofs with a straight edge and compass. You're learning how to bisect angles. You're learning how to create things and how to prove properties about things. And you can go back to Euclid's Elements and see exactly how all of these things were constructed a very long time ago. And of course, this older synthetic geometry has very practical benefits because you can use it for all kinds of engineering, which was what it was developed for originally. But synthetic geometry, is one of the most beautiful forms of mathematics. But it's not what we're going to talk about today because it's not really numerically focused. And in the 17th century, in the 1600s, René Descartes and Pierre de Fermat led the development of a new kind of geometry that merged this old synthetic sort of pure Platonic form with the newly developed mean algebra. And what they did was they said, okay, rather than dealing with these Platonic forms of shapes, relationships between the forms, those geometric shapes are going to be embedded in what we now call a Cartesian coordinate system. So we've got some axis, x and y, and we can represent these geometric shapes and points as numbers, as numbers and as algebraic formula. So we might represent a point as a pair of numbers, x and y, that tell it how far along the x and how far along the y-axis that point is. Or we might represent a circle as some function of f and y, or of x and y. So x naught minus x squared plus y naught minus y squared equals r squared. And that represents the Platonic form now embedded in sort of a numerical context. And so computational geometry, what we're going to discuss today, is about the application of computing power to solve statements about these geometrically, this combination of geometry and algebra. So we can take these algebraic forms representing the geometric shapes and solve them numerically. So it's really about a shift from a progression from the very abstract, proof-oriented synthetic geometry, which is likely a lot of what you've covered before, to a more concrete and answer-oriented analytical geometry. Okay, so again, I'm sure most of you already know most of the formulas. You know what the area of a circle is. You know how to calculate the area of a square, all of that sort of thing. So I'm not going to go into details on that. If you have questions, feel free to ask. what I'm going to go over is some of more of the details on how to effectively solve computational geometry problems. And computational geometry within the field of computer science has a very well-deserved reputation for being not necessarily difficult, but very tricky. It's tricky to get right. And particularly when you're solving your problems numerically on the computer. So there are two main reasons for this. So first of all, when you're given a computational geometry problem to solve, there's almost always lots of different cases that you need to consider. There's going to be tricky edge cases where if you leave them out, you'll get the wrong answer. So it might be, you know, are these 3 points collinear? What happens when there's a degeneracy in the system? Maybe a line I want to consider could be vertical. If I'm represented as a slope, that slope is infinite. It might cause problems in the computer. Or maybe my polygon has a concavity in it and my algorithm needs to be able to account for that. All of these sort of tricky edge cases that can cause problems when you're actually programming your solution. And the other problem, and this is a big one, I haven't talked about this much yet, is numerical stability. All right? So real numbers on a computer are not represented exactly. They're represented as floating point, that's fixed digit precision floating point numbers. And that means that some real numbers can't be accurately represented as a float. There's always going to be some rounding error involved. And when you're working with these complicated geometric formulas, that rounding error can cause big problems. So I'm going to show one particular instance that you might have seen before of when this numerical issue can cause problems. Who's solved a quadratic equation before? Everybody should raise their hand. I'm sure everyone's done this. All right? So ax squared plus bx plus c equals 0. There's two solutions, x1, x2. What are the solutions?
B plus or minus.
Negative b.
Negative b. Sorry, it's been a while.
Plus or minus.
Square root of b squared minus 4ac.
B squared minus 4ac.
All over 2a.
Over 2a. Yep, that is absolutely right. B squared minus 4ac over 2a. So there's two solutions, and there's a plus sign in one and a negative sign in the other. OK, so let's suppose you have some program that takes these coefficients a, b, c, and you're trying to get a solution x, where all of these numbers are floating points. What happens if you try and solve x1, where b is positive, and b squared is much, much bigger than 4ac? So maybe you've got b is 1,000 and a and c are 1. OK? Let's look at how this simplifies. So under the square root sign here, we've got b squared minus 4ac. But I just said b squared is way bigger than 4ac. So this is really b squared minus something small. If we take the square root of b squared minus something small, we get about b minus some epsilon. So we'll get b minus some very small number epsilon. OK? That's the solution to this determinant. Then we plug that in here, and we get negative b plus b minus epsilon all over 2a. The b's cancel, and what we want here is minus epsilon over 2a. Now, if you're representing all of these as floating points, this calculation ought to make you worry. So if we're holding these numbers as floats, that gives us a fixed number of precision. We've got some number of digits that are significant. Maybe we've got 10 significant figures here. So in b and in b plus b minus epsilon. So maybe we've got 10 sig figs and 10 sig figs here. But epsilon is much smaller than b. So if epsilon is small, that difference between b and b minus epsilon might be pretty far down there. It might be we might only have one significant figure for that difference. Or if it's small enough, we might have no significant figures for that difference. And when we do this subtraction, all we are left with is the number of significant figures for epsilon. So we can drop out and get this x1 to an arbitrarily bad precision. In fact, you can get an answer if you do this badly enough where it has no correlation whatsoever with the correct answer. And that's because you're subtracting very equal numbers as floats where the difference between them might be so small that you haven't captured it accurately. Okay? And that is true even though algebraically this is a perfectly correct solution. All right? And this is exactly the thing that you need to be really careful with when you're writing numerical solutions. Does anybody know how you solve this problem? It's a very straightforward way to do it. Anyone seen this before? Okay. So what we do is we algebraically rearrange this formula. I'm not going to show you the derivation right now, but we can take this and multiply and subtract and rearrange everything and rewrite that formula in an algebraically equivalent form as 2c over negative b minus b squared minus 4ac. This is exactly the same. You can work through it on your own and prove to yourself that these are the same representation. But now we won't have the same problem. Now instead of subtracting one number from another number that's very nearly the same, we'll be adding those two numbers together. And so we don't have that loss of precision, and we can get the answer to accurately rather than having our numerical problems come up. Okay? So you need to be careful with numerical stability, and nowhere more so than with computational geometry, because we've got a ton of these algebraic potential difficulties where you might run into this kind of problem. So some rules to improve your numerical stability when you're doing these. If you can, don't use floating points, because floating points are imprecise. Use integers if everything is an integer. When you're testing whether two floating point numbers are equal or not, don't use the equality operator. Have you done that before?
I've used the other way.
Yeah. So don't use the equality operator, because if there's some small error down in the 10th significant figure, and there's going to be some rounding error in your floating points, then that might tell you wrongly that those two numbers are different, even though algebraically they're equivalent. So instead, you set some epsilon accuracy, and you test whether the difference between them is less than that accuracy. Okay? And that epsilon is going to depend on whatever your application is. And then massage your algebra. And in particular, you want to massage your algebra so you're avoiding large numbers if you can. So factor out any squares and try and get rid of them if you want. That'll avoid overflow errors. And avoid subtracting nearly equal numbers from each other. That is a very good way to lose precision in your calculations. And if you're not careful with this, you can come up with answers that are arbitrarily wrong. So you do need to be careful with it. And more than, I know I say this every time I talk about a new subject, but more than any other subject, if there is an implementation of some problem you want to solve or some geometric primitives in your language, you should use it, because particularly for computational geometry. Because it will save you a ton of trouble trying to track down stupid little numerical bugs like this that are going to be really tricky to find. So if you have a quadratic solution solver, somebody else has already fixed that bug, and then you don't have to worry about it. So use library support, use implementations that you can find in your language. Okay? All right. So that is my warning for computational geometry. Let's talk a little bit about the actual subject. So there's two kinds of geometric primitives we're going to focus on. And again, we're going to work entirely in two-dimensional Euclidean space. Yeah?
It's not the most vicious solution, but couldn't you do like a binary search for the answer?
You can. Binary searches are also another good way to avoid those precision errors. If it's easier to check whether your solution is right than to generate the solution, that works really well. And actually, binary search and recursive algorithms are a really good way to solve computational geometric problems if you don't know the geometric formula that you're trying to work with, which is often a problem. If you look at today's homework, I set you a problem that involves calculating the areas of circular segments, which I doubt anybody remembers how to do offhand. I had to go look it up. There's actually a simpler solution, simpler to write, although slower to run, that uses recursive search to approximate the solution. So yeah, that's a very good plan. Okay, so we're going to talk about geometric objects. I'm going to focus entirely on two-dimensional Euclidean space. Most of this is easily generalizable to higher dimensions. I very much doubt you'll get anything non-Euclidean unless you're working in some abstruse mathematical field. But in general, so we're going to start off with points. Points are the basic building block of higher dimensional objects. So we can represent a point as an x and y coordinate, where those are the distance along the x and y axes from the origin, which is a point down here at 0, 0. All right, what can you do with points? First of all, very commonly you'll want to sort points. So if you have a list of points, you'll want to sort them so you can work with them in some particular order. Obviously, sorting points, you can sort first by x and then by y, or vice versa. If you're going to write a class for a point, which again, use an implementation if you can, if you're going to write it yourself, overload operators if your language supports it. So if you want to do sorting, overload your comparison operators. If you want to do addition of points, overload your addition operators. It just makes things a lot easier. And in particular, if you're testing equality of points, 2 points are equal if both the x and the y coordinates are the same. And like, what did I say about comparing equality of floats?
Use epsilon.
Use epsilon. Don't compare them directly, particularly for points. That causes problems. So use an epsilon. If you want to calculate the distance between 2 points, so suppose we have x1, y1, and then we have another point, x2, y2. What is the distance? Who can tell me that? Sure.
It's the square root of x1 minus x2 squared plus y1 minus y2.
y1 minus y2 squared. Absolutely right. That's the distance. One trick that I use quite a lot. So I work with three-dimensional computational geometry all the time. This is what I do for a living. And a very common trick is these square root are expensive computationally, and they are numerically difficult because they can cause some rounding errors. So if we want to compare two different distances, maybe we have d1 and d2, instead of calculating the distances exactly, we can calculate the squares of the distance and say, instead of is d1 greater than d2, we might say is d1 squared greater than d2 squared. This gives us exactly the same answer. We can just leave off the square root sign, and that can simplify our problem sometimes. So if you're working with distances, keep that in mind. Try to avoid the square roots if you don't actually need them. Does anyone remember how to do rotation of points around the origin? This is a little more complicated. You need to use a rotation matrix in terms of sines and cosines. I'm not going to go into it in detail. You can look it up in the lecture notes if you need it. OK. Lines. Line in Euclidean space is just a linear formula. So we'll write that as ax plus by plus c equals 0. So we've got three coefficients, a, b, and c. Does anyone remember the point-slope form of a linear equation? Yeah.
Y minus y1 equals b slope times
y, that's the point slope formula, which is fine. Y minus y1 equals x minus x1 times m, that one? Yeah. OK, so there's this formula. This is the point slope formula. There's also y equals mx plus b. This is the slope intercept form. Don't use these forms. Because this slope right here, what happens to it if you have a vertical line? What's that?
It's undefined.
Yeah, it's infinite. You have an infinite slope. And that doesn't mean anything. If you're working on it on a computer, your computer's going to crash if you give it an infinite, if you give it this. So we're going to use this formula. And you'll note that this is very similar to the slope intercept form. This number right here is the negative of the slope. And this number right here is the negative of the intercept. So what's b? B is a number that tells us whether the number or whether our line is vertical or not. So if it's 0, then it's vertical. And if it's 1, it's not. And it'll never be anything other than 0 or 1. So we'll divide it through to cancel it out. So use this formula for lines. Don't try and use one of these other ones. They'll fail on vertical lines. And I guarantee you, on problem statements, they'll give you tricky things like that that will make inefficient algorithms fail. Once we have a set of coordinates for a particular line we're working with, it's very straightforward to check whether the two lines are parallel. If they're parallel, A and B are equal for each set of lines. If C is also equal, they're the same line. If they're not parallel and they're not the same line, you can find the intersection between them by solving two sets of linear equations, which everybody should know how to do. OK, so that's enough basic stuff. Let's talk about a couple of common tasks, two common tasks that we'll have that you're very often going to see in a lot of computational problems. So suppose we have three ordered points. Call it A, B, and C. So if you're traveling from A to B to C, one very common question you'll see is, which direction do you turn at B to get from A to B to C? Are you turning counterclockwise or are you turning clockwise? So we could be turning left, we could be turning right, or we could just be going straight, in which case all of these points are going to be collinear. So let's define a function. I'll call it CCW on 3 points, A, B, and C. And we'll define it as, we'll take two vectors, AB and AC. That is equivalent to B minus A and C minus A. And we'll look at the cross product. So the cross product of these vectors is going to be, everyone's seen cross products before, right? Yeah. So we're going from A to B, from AB to AC, and right-hand rule. So you rotate from the first vector to the second vector, and the direction is the direction of your thumb. So this will give you a number that's either positive, negative, or 0. When is it 0? When they're in the same direction. And what does that mean for whether these lines are going left, or these points are going left, right, or straight? They're going straight. So if this is 0, then those points are collinear. What happens if it's positive? We're turning left, or counterclockwise. And if it's negative, then they're going right or clockwise. So very efficient algorithm, or very efficient method, and we'll use this all the time. Now, one interesting property, right here we're only looking at the sign. You can think of the magnitude of that cross product as the area of this parallelogram. And that ought to suggest something. Suppose we wanted to measure the area of the triangle ABC. What is that? It's half the area of this parallelogram, which is the cross product. So we can represent the area of the triangle ABC as B minus A cross C minus A over 2, which is much faster than trying to figure out, okay, what's the base of this triangle? What's the height of this triangle? That's going to be difficult to find. Using this, all we have to know is the positions of the points. We don't have to know any angles. We don't have to do any trig. It's much more straightforward. Now, an alternative way to represent this cross product is as a half of the determinant of the matrix of vertex positions. So we can write a matrix for all of these. So we'll say XA, YA, XB, YB, XC, YC. Does everyone remember how their linear algebra? You know how to do determinants? So you look at all of the rightward sloping diagonals and add them up, and then subtract all of the leftward sloping diagonals. So this is equivalent to, so we'll also write this area equals 1/2 of this determinant. So it's XA times YB plus XB times YC plus XC times YA, and then minus the other one. So minus XB times YA minus YB times XC minus YC times XA. And you can convince yourself that this formula is the same as this formula. You can work it out. And it's exactly the same algebraically. The convenience of this is there are functions, library functions, that calculate determinants of matrices. So you just have to steal one of those library functions, give it the point matrix, and you've got the area of the triangle. The other useful thing is this works for larger polygons. So if you have an ordered list of points, maybe you've got 4 or 5 different points, and you want to calculate the area of that polygon, you can just list all of the points in a matrix, x1, x2, down to xn, y1, y2, down to yn, and you'll calculate the determinant of that, take it and divide it in 2, and you'll get the area of the polygon. It's a much faster way to calculate areas of polygons than trying to cut it up into triangles and calculate the area of each triangle independently. Don't do that. Use the determinant. Now, the tricky part of that, you need to make sure your ordering is correct. They have to be ordered in the direction you actually want to go. So think about the case where you've got a square, and you know the positions of the points, and you want to calculate the area of the square. And we've got 1, 2, 3, and 4. If you order your matrix from 1 to 2 to 3 to 4, and then back to 1, you'll get the area of the square. But if you give the ordering wrong, you'll get something very different. So suppose instead you went from 1 to 2, and then you put 4 first, and then 3, and then back to 1. Now you've got the area of something very different that is not what you wanted. So you need to be careful when you're doing this determinant method to make sure that you've got the ordering of the points on your polygon correct. OK. Let's talk about our only algorithm for the day. This is called a convex hull problem. And it's a very useful problem. And the definition of a convex hull is you have some number of points. We'll start with n points. And we want to find the smallest convex polygon that contains every point. So the smallest area and has to be convex. And that's equivalent to saying if we walk along each point, along a vertex of that polygon, in order, we'll always be turning in the same direction. We'll never make a left turn and then a right turn, or a right turn and then a left turn. We'll always be turning right, or we'll always be turning left. That's a good definition of a convex polygon. Okay, so if I give you, a distribution of points like this, you can just look at it right now and say, okay, well, here is the convex hull. These are all the vertices on the hull. And all of these vertices on the interior can't be a part of the hull, because if we tried to add them, now this is not a convex polygon, and now this is a concave polygon. Because here we're always turning left, but then this angle is a right angle as we go around the polygon. So that is a concavity, and we can't have that. So the question is, given some number of points, how can we efficiently calculate this? Well, so here's an interesting fact. If we take some edge between 2 points, maybe we'll look at this edge. So from A to B, and then we look at the direction of turn from A to B to every other point. Which direction are we turning to get to here? Left. 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 Right. Now, okay. So anything where you've got both left and right turns, that's an interior edge. That's not part of your convex hull. But if we look at another edge, maybe we look at A, B, and we go from A to B. Now, which way are we turning? Left. So we're going A, B, left, 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 left. So if we find all of the directions going the same way, that edge is in the convex hull. So that gives us a very straightforward order n cubed way to find it. We look at each pair of points, look at the edge between those points, compare the angle between that edge and every other point in the list, and if they're all going the same way, we put that in our list of edges that are in the hull. And we keep doing that until we've got all of the edges that are in the hull. And that works just fine. It's also kind of slow. We don't really like cubic solutions. So let's think about a faster way to do this. Suppose, so for any list of points, there are always at least 2 points that we can guarantee are in the convex hull. And let's start off with the leftmost point, so the point with the smallest x value. I can prove that this has to be a part of the convex hull. And this is how I'm going to prove it. Suppose that it weren't a part of the convex hull. Then it would have to be an interior point, and that means that there's some edge that is to the left of that point, so that it can be inside. But we know this is the leftmost point, so any edge between any other 2 points is going to be to the right of it. There's no way to get an edge to the left of it. Therefore, it's not an interior point, and we know it's in the convex hull. So that means we can take the leftmost point and start with it. That's a starting position. We know it is in the convex hull. And then what we're going to do is this. We take that, we're going to call that one point 0. And then we're going to draw an edge between that point and every other point here. So there's that one, that one, And then we're going to sort these points based on the slope of that edge. OK? And so we'll number these based on that slope. So we'll start at 0 and sweep through, keeping our elbow here at 0, and sweep through all the other points and number them in that order. So this is point 1, point 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And how long does that take? How long does the sorting take? What's that? That's what I'm trying to get at. How long does a sort take? N log n. OK? You can use whatever kind of sort you want. Heap sort works fine. You can't use, it would be really nice if you could, but you can't use like a radix sort or a bucket sort because the slopes are all real numbers and they're not going to work that way. Yeah. Yep.
Edge case, let's say there's a tie for leftmost point, and one of the slopes is thus infinity.
If there's a tie for leftmost point, it doesn't matter. You can pick one of them. They're both guaranteed to be on the hull. So you can just pick one. And if there's a tie for slopes, then all you have to do is you start with the leftmost one and then go to the rightmost one.
So basically, if you get a vertical slope, then that means that point's on the hull anyway?
Well, so if you get a vertical slope, then suppose you have another point up here that's perfectly vertical. We can either pick that one to start with or pick this one to start with. If you pick this one to start with, this slope is essentially positive infinity, so this will be the last one. If you pick this one, this slope is negative infinity, so this is the first one.
Okay, so as long as your algorithm can return positive or negative infinity and differentiate between the two.
It should work fine, yeah.
What if there's a point that's, you know, like on a whole line? Does that count as a whole point, or is that?
What do you mean on a whole line?
So if you have 3 collinear points all the way on the left.
Like here, here, and here.
Yeah, can you just use the top 2 or the top bottom?
You pick. I would probably pick the top one, and then put the next 2 in order of y as you go.
This is actually kind of a question about the problem, which is that does it need to contain the middle one, or could it just be the top or bottom one?
You know, it's going to depend on the application, because it might be that you could define these 2 as vertices, and this would be an interior point, even though it's not really interior. It's going to depend on what you want to solve for. If all you want is the polygon, I mean, one is as good as another. It's exactly the same shape if they're exactly collinear. If you want the points that are actually on the edge of the polygon, you might want to explicitly do that. OK. So now we've got our ordered list of points. So here's what we're going to do. We're going to draw in edges of our convex hull. So we start at 0, and we draw an edge from 0 to 1 and from 1 to 2. Now, because we're going in this order, which direction should we turn for each new point in the convex hull? We're always going to be turning left. All right? So we're going to check this first turn from 0 to 1 to 2. That's a left turn. That means we're good. So then we're going to add another edge from 2 to 3. And that's also a left turn. So we're still fine. So now we'll add the next edge from 3 to 4. And now, which way are we turning? We're turning right now. So this is bad. So what we do is we don't remove the point we just added. Instead, we go to the point just before that. We say, OK, 3 must be an interior point. So we're going to remove those edges from 3 to 4 and from 2 to 3 and replace it with an edge from 2 to 4. And now 1 to 2 to 4 is still left. So we're good. So then we go on to 4 to 5. And we've got a right turn again. So we do the same thing. We say, OK, 4 is an internal point. We're going to go from 2 to 5. And then same deal. 5 to 6, still good. 6 to 7 is bad. So we remove those and go from 5 to 7. 7 to 8. Now, again, we've got a right turn. We remove those and then 5 to 8. And we keep doing that. And as we go, we've got a list of vertices where we've been continuously turning left, and everything is inside it. And so what we'll end up with is this final polygon. So this is called Graham's scan algorithm. And what's the runtime complexity? Yeah?
Before you process, you need to check more than one previous point until.
So you need to keep checking. Yeah, I should have kept that case. It's every time you need to check which way you're turning, and if it was right, you delete the point just before the last one.
It's not only the point before, but all the points before that.
You keep checking it until you're turning left. So you might have to delete 3 or 4 points, or however many points. Yeah, absolutely. Okay, what's the runtime complexity?
It depends on the shape, but it's.
No, it doesn't depend on the shape, actually. It's just n for the scan.
Yeah, once you go.
So that means that the sorting is going to dominate it. Okay, so it's order n log n, which is way faster than the naive order n cubed. Now there's another trick to this that can let you cut that down even more. So I told you that the leftmost point always has to be on the hull. Which other points also have to be on the hull?
3 other, rightmost.
Yeah, so the rightmost, the uppermost, and the bottommost. Now, in some cases, there's only going to be 2 of those. So if the upper and rightmost are the same, and the lower and the leftmost are the same. But usually, you'll have at least 3 and sometimes 4. So what you can do then is take those 4 or 3 points and draw the polygon connecting them, like that. What does that do?
It eliminates points.
Yeah, everything that's inside this quadrilateral, you already know, without doing any scanning, that they are necessarily interior points. So you can ignore them. You don't have to sort them. All you have to consider are these ones that are outside of that quadrilateral. So that can cut down on how many points you have to consider and get you even faster than n log n. Particularly if you're doing this in high dimension space, or if there's a lot of points. You know, if you've got 10 million points and you can exclude everything in the middle, that might save you a ton of time. So that's a very good idea to work with. Okay, so that's computational geometry. Again, this is called Graham's scan. Convex hull is going to be a really useful problem. So I've set you a fairly difficult homework problem today. Please don't put it until the last minute. So if you look at my homework solution for this last week's problem, the solution that I gave you is about 16 lines of code. The solution that I wrote up for this problem, this next week's problem, is about 2 pages. Okay, there's a lot of special cases that you're going to have to consider, and it's some fairly complicated geometry. So please don't put it off to the last minute. All right. So other thing. Next Friday is going to be a different kind of class. We're not going to have a straightforward lecture. We're going to do practice competition. I'm going to work out the details of exactly how that's going to work with the TAs. Please show up on time. We are already kind of time limited in the class, and I want to give everybody enough time to at least get through 1 or 2 of the problems that I set. And again, this will count as one of the practice competitions that you need to do for the class. So this is going to be the easiest one to do for the class. Please just show up on time. We're going to start at 11:45 sharp, get everything going. And I'll see you next week.